This is Karen O'Brien, and I wanted to do a short video with you called Start a FLO-2D Project, where we take this tutorial, the self-help kit, and we just start the first few lessons of it. So it'll give you an idea of where to get our documentation. For example, if you're on our homepage, you can go to Docs and get access to this project. So there are instructions for installation and setup. There's the user manual for the FLO-2D plugin, the FLO-2D Gila plugin. This is the older plugin, and there are these tutorials. So this is the self-help kit for FLO-2D Gila, which is the name of our plugin that creates project data. You get the self-help kit setup. That'll just setting up your computer to run and get started with this project, and then create a project in Grid. We'll be starting here on Create a Project in Grid. Now, if you're using the older documentation, it'll be mostly videos that show you how to do these. But in our new documentation that we hope to release in December of 2025, you'll see that we have expanded our tutorials to include text on these different training package or these different tutorials. So create a project in Grid, hydrology, channels, everything will be step-by-step instructions using text. Now, I'm going to start by going to this simple project overview. So this is a complex urban model that has a channel, culverts, storm drain, and rainfall and infiltration. So it's a relatively complex model, but we're going to start with just the bare bones of this. We'll call it the skeleton. Now, what I have here is a different QGIS window where we can start fresh. And I also have this QGIS Lesson 1 folder, which covers setting up the grid and doing the hydrology. So inside here, we have a shapefile for the overland roughness, a shapefile for the project domain, and an elevation raster. I'll drag and drop those onto the project, onto the map, and click OK to set the transformation. And then you can see here that our coordinate system has been changed and updated to match the coordinate system of our data. Now, at this point in time, all of my data is in the same coordinate system, and that's a good thing. Let me move this one down. Let's see, that right there. So this will be our project domain. This will be our overland roughness, and this will be our elevation. Let's start by, we can turn this one off actually, because we won't be needing that right away. Let's start by clicking New Project, New FLO-2D Project, and then we'll create that project. Let's call it the Self-Help Project. And that is a geo-package. And a geo-package is a set of tables and geometries that represent your project on the map. Now with FLO-2D, we have specific layers that are pertinent to FLO-2D projects. And what it's doing right now is it's building an empty set of tables so that we will start filling that in with the project data. I'm going to pause until it's complete. Now that the geo-package is created, you can start filling in the data. And the first thing that you have the opportunity to fill in is some of the project data. So you could put some information about the project or about who created the project. You do not need to set the cell size at this time. That will be set somewhere else. But you can, if you want, set the limiting Manning's N number. This will be like anything that you don't add to the Manning's N grid, this will be the default for it. And then click OK. And now we are requested to determine whether or not we want to add external data to the project or leave it as external data. If I click yes, I can take two of these layers that I want to stay with the project and move them over to the left-hand side of this table. And if I click OK, that will copy the Manning's N and the elevation to the geo-package and then add it to a group called external layers. Now, I do not need to add the project domain to external layers because the project domain will be copied into comp domain, and then I can just remove that layer. So we are now finished with this one again for now, for the time being, and we can start to create our grid. So if you come over to the Grid Tools widget here, you can click Create a Grid, and change this to external polygon layer, select the layer, and then set this field to cell size. That's important. Click OK, and that will start to create your grid. I'll pause till it's finished. So once the grid creation and grid checks are complete, it will give you some information, the time it took, that should be different on every computer, total number of cells, and the cell size. Now we're actually finished with this layer, so we don't need it anymore. I'll just do right-click R or right-click remove. And you see here that that layer was copied to the computational domain layer. You can only have one layer in here in computational domain, only one grid polygon. And what it does is it just sets up the grid inside the boundary of that polygon. Right? If you want to get back to zoom layer like that, you just select that layer and zoom to layer. And now we can start on elevation. So the elevation button here, you see there's only one raster, so it points right to it. And we don't need to do anything else. If you want to use an average or bilinear, whatever you want, just pick it and click OK. And that will warp the elevation from this raster to the shape and size of your grid, and then sample the elevation from your grid. So the elevation raster is kind of the one thing that may not necessarily need to be in the same coordinate system as your project because it uses a GDAL warp to get the data from its source data into matching your project data. Once that's complete, you will see that we now have elevation data assigned to our grid. So we have a 30-foot cell size, and I'll show you if I use this button right here and click on one of these grid elements, you'll see that we have a 30 by 30 cell size, grid element number, grid element elevation, the N value, which right now is default, cell size, and number of cells. I'll turn this elevation rendering back to nothing so that you can just see the grid. The next step will be to set the Manning's roughness for the overland grid. So if I turn this back on, I can go to this button right here, which will process roughness from polygons. If you have an elevation raster, or sorry, excuse me, if you have a raster that processes your roughness, you can use this button instead. So, and then here I have a source layer, which is Manning's N, and a roughness coefficient field, which is N, and I can either do an area weighted average of all the polygons that intersect our grid, or I can do a centroid point sample. I'm going to choose that one because it's faster. I'll click OK, and then we'll wait for that to complete, and I'll pause the video until it's done. Once it's complete, you can click OK, and now we're finished with this layer. We're also finished with this layer for the time being, but if you want, you can set it to hillshade. I just double-clicked it, set it to hillshade, click OK, and it makes it look a little more like what your project would look like. And this is just the LiDAR elevation raster. So take in elevation data, take out all the trees and buildings and things like that, and process it into a elevation raster. The next thing that we want to do is to add rainfall to our project. So if I go down to the rain widget, I can check on simulate rainfall, and we can set this to a rainfall value. 2.65 inches, if you are using a metric model, it will be millimeters. If you're using a English model, it will be inches. So 2.65 inches of rainfall will be uniformly distributed across this grid at a time series, at a given time series. To get to the time series, you'll click this button here, which should take you to your time series folder, but if it doesn't, that would be C drive, users, public, public documents, FLO-2D Pro documentation. I renamed mine to 1, FLO-2D Pro documentation, and then rainfall distributions. And we'll be using a 100-year, 6-hour pattern, and click open. And now you can see that this is the rainfall pattern or data on the left, and this is the rainfall pattern on the right. And as you can see, it's just rainfall intensity, where we have time in hours on the left and percent total of the rainfall that is applied to the grid on the right. And our percent total is not 0 to 100, it's always 0 to 1. The rainfall is now complete for the uniform rainfall. There are more advanced ways to do rainfall modeling, so I suggest that you go to the to the different tutorials to watch how to set up the different types of rainfall. Now we have rainfall. Now what we want to do is to apply the discharge that will be crossing our boundary. So what I have is an inflow hydrograph for the water that is coming down this drainage channel called Cave Creek and crossing into our basin called the Grover Basin. And we can do that by setting up a boundary condition. Inflow node, we'll check that, and then we want to use a point boundary condition, and we'll just put it somewhere in here. Click on that. It is indeed inflow, and click OK. And I'll zoom in here so you can see that it's just set to one of these grid elements. If you don't like the position, you can change that to the node tool and move it. Doesn't really matter, just so long as it's somewhere in this general area. Come back over here, and you'll want to click this button again to save the data in the layer right here and load the data in the widget. This is indeed a floodplain node, and it is an inflow hydrograph. We want to set it a time series. So we'll name this time series. This will be the 100-year 6-hour pattern or 6-hour inflow hydrograph. And also we will change the name of this one to Grover Inn. And click OK. And now we need the data. Back in our project, we have the Grover Basin Inn. And here's your 6-hour pattern, right, or 6-hour inflow hydrograph right here. And what we have in our 6-hour hydrograph, if I do Control A and Control C, is tab delimited data. On the left is time in hours, and on the right is discharge in cubic feet per second. And of course, if this was a metric model, that would be cubic meters per second. Put that into the table editor and paste it, and now we have an inflow hydrograph on our project. The last thing we can do is schematize that, and that will convert that from user data to FLO-2D data, and that's that green grid element. That just means that we assigned this hydrograph to this grid element. Okay. The next step will be to do a downstream boundary condition. In this case, we have two downstream boundaries that kind of need an outflow condition. One of them might be right here, this basin, and one of them would be this, but now this will become a channel eventually, but while it's a floodplain, we'll set it up as a floodplain outflow control. And then when we convert it to a channel, we would just modify that to a channel outflow control. So here is our boundary editor again, but this time we'll use the outflow side of the editor, and we'll use a polygon for the basin. We'll just drag a polygon where we want to apply our downstream boundary, and then we click Save, and let's just call this Turtle Out, because this is the Turtle Rock Basin. So we'll just call it Turtle Out. And then we'll set this to floodplain outflow, no hydrograph. And the next one we'll do is, whoops, I did not mean to change that. I was on the wrong one. I was trying to pan with my arrow key, but because I was selected on this thing, it moved that instead. So now the next thing we want to do is add a polyline feature here where we want this flow along our channel to leave the boundary at normal depth flow. Again, it is an outflow condition, and we will hit the Save button right here after we create this line, and this will be Greenway, and then we'll call this Overland Out. And this will be replaced when we put the channel in. We'll just delete this one and replace it with a channel out. Okay, for now, this will be floodplain outflow, no hydrograph. And the last thing that we want to do is to run the schematize button, and that will, again, convert this user data into FLO-2D data. And you can see right here that this outflow condition has been set per this polygon, and this outflow condition has been set per this polyline. You can also do it with points. Now, if you want to clear this rubber band, you can click this button right here, and that will clear the rubber band, because otherwise that rubber band will stay there until you do something else that requires a rubber band. And then we're finished with the boundary condition editor, so I will minimize that. And the very next step will be to add, let's see, we have the grid, elevation, Manning's N, rainfall, boundary conditions, and the final step will be to add the infiltration, and then we can save and run. Here's your infiltration editor down here, and we have 3 types of infiltration for FLO-2D: green and amped, global SCS, where you apply a curve number, and global, and Horton, sorry, not global. You can do global or spatial. So if you choose global only, that will just apply the global green and amped using these parameters. Hydraulic conductivity, soil suction, etc., and just applied globally. So I'm going to select green and amped and click OK, but I don't want global infiltration. I want spatially variable infiltration. So I need to use the Calculate Green Amped button right here. And we have 2 options. You can either calculate from these layers right here, where you can see we have a lot of different data samples in here, or so you can use the land use shapefile, the soil shapefile for the 2018 method, or the soil shapefile from the 2023 method, or you can use the Surgo data, where you download online data to calculate the soil and land use data. Calculate the soil data from the Surgo method, or you calculate the land use data, which is just like your imperviousness and, your initial saturation conditions and things like that from the OpenStreetMap data. So let's click Calculate on this one. And I'm going to pause the video once this starts loading, but I want to show you that basically it just starts downloading the data, and then it will process it into green amped parameters. Okay, the processing is done for soil, and what it did is it set up the fields for this layer that it just added. So you can see the fields are set up right here. Now we can do the OSM data. So again, we click Calculate, and I will say yes, because I don't want those immediate layers. I just want the final layer. And that will now go onto the OpenStreetMap and download OSM data as rasters, and then process that into a polygon. I'll pause until that is complete. And as you can see, the last step is to vectorize the land cover map and then remove all those unneeded layers. And the final step will be to run the calculator. So we just click OK, and that starts the calculation process. And then again, I will pause the video so we don't have to sit here and wait for this. But what it's doing is it's taking a group of cells, processing them, and then moving to the next group of cells. So regardless of how many grid elements you have in a model, it doesn't take that long to process data. And so it's a fairly efficient system. Okay, now it says that calculating the green amp parameters are finished, so we'll click OK. And the final step would be to save the project, because, as you can see, these 2 layers are scratch layers. So if we want to save them to the project, just click Save and Yes, and again move them over to the left-hand side of the map and click OK. And as you can see, they are no longer scratch layers, they are now permanent layers, but we don't need to see them anymore, so we can uncheck them and continue with the simulation. Continue with the processing. Now we're finished with green and amped infiltration, so we can collapse that. Or if you have one of these opened, you can collapse it here. What I don't recommend is you use the roller wheel in here to move this up and down, because it will change values, okay? So instead of using the roller wheel, we want you to use the drag bars on the left and use the collapse before you move between processors. Let's go ahead and do the setup. So if I go to FLO-2D parameters, and I can do setup control parameters, the cont.dat control parameters are on the first tab. The taller.dat control parameters are on the second tab. Let's go ahead and start with the time control. Let's say this is a 6-hour rainfall pattern for the 100-year event. So if we run it for 10 hours, that should give our project ample time to drain. And we can leave this to 0.1 output interval. That's a good output interval. We can either keep this on text screen, which will just run the simulation, or we can set it to detailed graphics, which will give you an opportunity to watch the simulation run, but it takes quite a bit more time to complete the simulation. So I typically use text screen. We can put it on detailed graphics just to give you some more, so that you can see it. This is an English project, meaning that is in imperial units. So the two switch positions are English or metric. So it'll be imperial units, this will be SI units. I'll minimize that and move on to, we don't need any global modification at this time, so we'll keep that minimized. We do need to make sure that our rainfall switch is on and our infiltration switch is on. And as you can see, if you hover over these switches, they will give you a little bit of information from the data input manual on how to use the switches. At this point, we don't have any other switches. We can minimize this, but we do have some time-lapse output. So if you want to use time-lapse output, you can set this to timdep.htf5 or timdep.out and uncheck this and set this to 0.1 or 0.5, and that will give you time-dependent output data, time series output data. And you'll click Save, and now the project is ready to run. So what we can do is a quick run. Right here are the FLO-2D settings. You got to be careful that the first thing that you do is check that the FLO-2D folder is set up so that it can go find your engine to start the simulation. Now, if I click Quick Run, what will happen is we'll go to the Run folder, and we can select the FLO-2D Lesson 1 Complete, and we can check that we are running the data files and go ahead and start the simulation. Now, what it's just done is it's exported all these DAT files into the Run folder, and now the engine is going to go find these DAT files and run it. So what we've done is we have decoupled the project run from QGIS. Okay, so FlowPro Engine does not use QGIS to do anything. All it does is it goes and finds its DAT files and starts the simulation, which you can see here. Now I will minimize this. Well, you can start to see that we're seeing a little bit of inflow here, and we'll start to see a little bit of rainfall in a few minutes. Right now, everything is being infiltrated. So then I'll minimize this. And let's go ahead and go to that output folder that we just created. And let's go, that will be FLO-2D Run and Lesson 1. And I will sort this by type, and you can see that these are the DAT files that were created, and these are the output files, and all of this data is ASCII. So let's go ahead and return to the simulation. And you can see now that we have a little bit more rainfall and a little bit more of the inflow hydrograph is kind of coming onto our map. Not much, really kind of takes a while for things to get kicked off. We're just at the very early stages of the simulation at this point. And I think right now I can just stop the video, and you should be able to complete this project on your own if you want by, again, going to the tutorials and getting the access to the Create Project in Grid and starting Lesson 1 on your own. So if you have any issues or problems or want to see more about this, go ahead and contact me, Karen at FLO-2D.com, or use our contact form on my website to contact us. Thank you.